Thank you very much. Thank you very much for the kind invitation and hospitality. So today I would like to tell you about the property of modular invariant partition function for Calabi-Yau compactification. From a perspective of mathematics, it has to do with how to construct a modular invariant combination of objects which include the mock modular form. The mock modular form is very close to modular form or Jacobi form, but there are various ways to think about it. One way to think about it is to start with weak mass form, which is an eigenstate of Laplace operator on upper half plane invariant and SL to Z, satisfying certain set of conditions, and you just take the holomorphic part of that. And what it does is that if you take a modular transformation, it's not completely modular, but there will be an additional piece that comes out. And that has some physical interpretation that I will tell you later. The history of mock modular forms is very interesting, and I cannot resist telling you about. So I think that it was Ramanujan who was studying it in his last year in India in 1920. And he wrote a letter to Hardy describing 17 examples of what is now called mock modular form of weight half. And then it arose some interest. For example, Watson, of Whittaker-Watson, chose this subject as his retiring presidential address of London Mathematical Society. But then there was his lost notebook, which is more fascinating. He had a large number of notebooks, and that was after his death donated to the University of Madras, who sent it to Hardy, who couldn't figure it out, and he passed it on to Watson. And then when Watson died, Whittaker gave it to Rakin. But he subsequently donated to the library of the University of Cambridge, Trinity College, because that was where Watson's other paper were. And then in 1976, George Andrew rediscovered his notebook and then started studying it. And then I think 10 years later, 1987, this notebook was published in December. And so actually, in December of 1987, I was visiting India to give a set of lectures in the winter school in Kanpur. And then that was it the centennial of his Ramanujan, I guess? And then the book was published, and there was a big TV documentary on that subject. And so I was watching that with Indian friends like Ashok Sen, Gautam Mandar, and Spent Wadi, and joking, maybe one day it's going to be relevant to string theory. And I didn't realize that exactly around the time the relevance of that string theory was realized, because Eguchi and Taormina was studying character of n equal 4 superconformal algebra corresponding to compactification of string theory on K3. And subsequently, Eguchi's student Odake generalized this for general Calabi-Yau manifold. And so you have extended n equal 2 superconformal algebra. Extended, I mean that in addition to the standard n equal 2 superconformal algebra for string compactified on Calabi-Yau manifold, you can have a symmetry generated by spectral flow, which I will tell you a little bit more about that. And then, so those people computed the character of n equal 2 extended algebra. So basically, it's trace of q to the L0 minus c over 24, and then y to J0, where J0 is a U1 charge associated to this n equal 2 superconformal algebra. And then there are two kinds of representation. One is called non-chiral, which is basically non-BPS. And its character are characterized by the U1 charge and the highest weight of L0, and of course function of Q and Y. And these are very simple things. These are basically oscillators. depending on ns and or r, you have integer or integer plus half. And then you have a bosonic oscillator. So those basically come from the n equal to descendants of n equal to generators, and this is from Virasoro generators. And then in addition, there is a sum over precise form of this is not so important, but I'm just writing this so you know that there are explicit formulas. So this sum basically comes from spectral flow. And then you have, I guess I should write Q to the delta also. So this is a very simple thing. This is basically theta summation, and then there are oscillators associated. So this is a partition function for a non-chiral sector. So non-chiral sector partition function is extremely simple, but chiral part is more interesting. So you can call that as BPS. So delta is restricted to this BPS condition. So then the character for this representation is given by, again, this oscillator form. But then the reminder is interesting. The sum over spectral flow has an interesting form. So this is, it turns out to be one of the mock modular forms, or mock Jacobi form in this case. So what happens is that BPS part, BPS character transforms. So this one transforms rather nicely under modular transformation because you have this simple product term, and this is a theta sum. So non-BPS one transforms among themselves. The BPS character transforms it in itself, plus some junks in the mock modular transformation, which can be described by non-BPS object. So the task of understanding the structure of the Hilbert space of conformal field series whose target space is Calabi-Yau is to construct a modular invariant partition object out of this mock modular form and regular modular forms. So that mathematically, that is a question that I would like to address today. And so, of course, understanding modular invariant combination of character is one of the part of the program of understanding conformal field theory in general. And I have chosen to talk about this today because for two motivations. One is that in the case of any supersymmetric field theory, a lot have become understood in its BPS sector. So of course, in the past few years in particular, there has been lots of progress in understanding supersymmetric part of supersymmetric theory and superconformal theory in diverse dimensions. And those are very interesting. But very little is known about its non-BPS sector. So I wanted to say something non-trivial about non-BPS sector of any supersymmetric theory. And this is one of the situations where I can say something non-trivial about it. There is another interesting question, which which I'm not going to address, but I'm going to raise it anyway, and because that was one of the motivation of us, and we may say something that may be relevant to that, which is a question of how many topological types are there for Calabi-Yau manifold? So are there infinitely many topological types, or are the topological types bounded? So for example, in the case of a two-dimensional Riemann surface, we know that there are infinitely many topological types characterized by the genus. Genus goes from 0 to infinity. So you have infinitely many topological types. It's not known whether there are infinitely many topological types of Calabi-Yau or not. And of course, this question has obvious relevance to the string theory question of landscape, for example. There are infinite landscape or finite landscape, for example. And so, for example, one obvious related question is that is a total Hodge number, is a Hodge number bounded? So people have constructed many examples of Calabi-Yau manifold. For example, recently, Watty Taylor has been systematically studying elliptically fibered Calabi-Yau manifold, and he seems to claim that for elliptically fibered one, the largest Hodge number H21 is 492, for example. And he claimed to have a proof that there is nothing larger than that. So that's an interesting question. So I'm going to, so in case you fall into sleep or some other reason, I would like to give you the one of the results that I'm going to present. So basically, we are interested in computing the partition function, which is a BPS part. In fact, it's the sum of half BPS part and quarter BPS part and the non-BPS part. So this is a partition function for 2D n equal to sigma model, whose target space is Calabi-Yau default. What I'm going to say applies for D equal 2, 3, 4, and 5. And we haven't figured out how to do it greater than 5. And so this part is completely understood. This part can be understood by knowing just Hodge number. This part is essentially understood by knowing the elliptic genus. So this is a question. This is a part that I'm going to talk about today. And then, so one of our results.
Quarter BPS, you mean BPS on the left but not on the right, or vice versa?
Yes. And so one of the results I'm going to present is this. So for example, for Calabi-Yau threefold, suppose H11 plus H21 is large, and I'm going to quantify precisely what I mean by large. This is somewhere along the size of this largest Calabi-Yau known. For example, Watty Taylor has this upper bound of 492, I suppose. And our result applies to some Hodge number somewhere around or larger than that. And so then we say that there is non-chiral, non-BPS state whose central charge, whose conformal weight, left conformal weight plus right conformal weight is less than 2/3. So you have an operator whose dimension is relatively low because, for example, the first non-trivial half BPS state has conformal weight 1. So this is lower than that. So you have, if you take delta plus delta bar, of course there is a vacuum and there is a 1, which is the first non-trivial BPS state. And then, so I claim that there are non-BPS states below 2/3. And moreover, the number of them, number of such non-BPS state grows linearly in total Hodge number. So I'm going to provide those numbers later. So there are precise numbers to it. And so this is interesting because that means, well, I do not know how these non-BPS states are distributed in this domain. But suppose if they are, for example, relatively uniformly distributed, so then it would mean that if you increase the Hodge number of Calabi-Yau manifold, it becomes denser and denser and become continuous in the limit of large Hodge numbers. And well, one thing that one may imagine happening may be that the Calabi-Yau decompactifies. That is that you are forced to have a large volume of Calabi-Yau if you want to have a large Hodge number. And this is not, this may be reasonable because we know that in lower dimensional case, that if you normalize the metric of the space in an appropriate sense, then there is roughly some fixed number, a fixed amount of volume per topology. So for example, in 2 dimensions, if you normalize the metric of the surface to be proportional to Ricci curvature, which is maybe reasonable, then it's obvious that the volume of the Riemann surface is proportional to the number of handles. So if you want to increase the number of handles, the geometry grows. And so maybe there is something like that for Calabi-Yau manifold. But so another thing I should say is that this is not the optimal bound. In fact, as you see in my presentation, that this can be much improved if we do it more systematically. So it is my hope that I can maybe lower this further. And if we can show that, in fact, it hits 0 at some Hodge number, that would be the signal that there is an upper bound for the Hodge number. So that was our original hope, in fact. How much time do I have?
Yeah, usually we had 1 hour and a half. But
oh, okay.
1 hour usually. The logical
sure.
But you
okay, yeah, well, I mean, I don't think I need 1 hour and a half, but I might need a little bit more than, I might go over 11, that is.
That's fine, we can do it.
Okay.
But usually we take a break.
No, but
Sure.
Depends on the structure. If he thinks his break is suitable with his stuff, we'll go.
Otherwise, we
Yeah, this might be a good place to break to begin with.
So may I ask questions?
Sure, please.
This number you said, the right-hand side, and the number of the non-BPS state. Are there any mathematical interpretation of this number?
Yeah, this is a limit of some ratio of objects that you can construct out of mock modular forms. So there are some functions that I can construct, which I'm going to denote G and gamma. You take a ratio and then take some limit.
Well, I mean, for the Calabi-Yau manifold,
Yeah.
the DPS state can be somehow some kind of eigenvalue of some operators, or?
Yes. Oh, yeah. That's a good point. So in the large, if the size of Calabi-Yau is much larger, I'm doing 2-dimensional conformal field theory, which means that we are doing essentially string theory. So there is a length associated to size associated to this surface, this problem. And if the size of Calabi-Yau is much larger than that, then you can evaluate delta plus delta bar as eigenvalue of Laplace operator. And so that's why I was talking about the volume, because then if the volume becomes large, the eigenvalue of Laplacian becomes sort of continuous. And but that's an approximation. So if the size of Calabi-Yau is large, then parametrically for large Calabi-Yau, you can approximate that by the value of eigenvalue of Laplacian. But there are corrections to it. And if the size becomes smaller, then the correction becomes large. And the other thing I should probably point out that this is a global bound. So for each topological type of Calabi-Yau, you have this kind of bound for any value of moduli of Calabi-Yau. So let me give you a simple example. Suppose, for example, the target space is S1. Target space is S1. Then we know that suppose the radius of radius is R. Then of course the eigenvalue of Laplace operator goes like 1 over R square. So you have n square over R square. So R becomes large. Then you have low-lying eigenstate. Now, as R becomes small, there are string winding states. So that means that delta plus delta bar, you can have n square over R square, or you can have m times R squared, where m is an integer. So when R is large, this one is smaller. And when R is small, this one is smaller. And then at the so-called self-dual radius, when R is of order 1, they becomes a similar order. But in all cases, delta plus delta bar is bounded by 1. the other way. So that you can show that there are always, whatever the value of R it is, there are always delta plus delta bar, which is less than 1, less than or equal to 1 in this case. So this number is analogous to 1 in this case. Okay? Yes, Martin?
In the K3 case,
Yes.
I mean, we know the Hodge numbers.
Yes.
How does this story work there?
So I'm going to tell you that.
Okay.
Yeah. Any other question so far?
And presumably what you're telling us will not work for non-compact Calabi-Yau.
I'm going to use compactness. Yes. Non-compact case, actually, the use of modular invariance, etc., is more subtle. And also, elliptic genus will be different depending on the boundary condition at infinity. So I should also point out that this work was also inspired by the earlier work by Simeon Hellerman and also his collaborator. Although the technique I'm going to use in the end, so initially we employed the technique they developed, and but now we found that actually you can get a different and interesting bound by employing different type of techniques. And so I'm going to be describing mostly this new way of thinking about it. And the other difference is that so Simeon and the very interesting and powerful result for general conformal field theory. And here I'm going to sort of apply the idea along the line, but in conformal field theory with this structure. So that means that we can actually take advantage of known result on BPS sector and use that to understand non-BPS sector. Any other question? Okay, so let me move on. So now I'm going to give you so this was the sort of outline of what I want to tell you. And now I would like to tell you a little bit more detail. So we are interested in n equal to CFT in 2 dimensions. Which is described by a sigma model whose target space is Calabi-Yau default. So that means that you have n equal to superconformal symmetry generated by Virasoro algebra and 2 conformal generator and U1 charge. But in d-dimensional Calabi-Yau, there is a unique holomorphic D-form. So if you have such an object, then there is a corresponding operator for 2-dimensional conformal field theory. And so this is the famous spectral flow operator. And this operator is important because this is actually the origin of space-time supersymmetry in the non-compact directions. So when you use a sigma model to construct a supersymmetric compactification of string theory, then it is this operator that gives you the map from NS sector to Ramon sector. So in particular, if you have this, then there is an isomorphism between Ramon sector and NS sector. And so for example, if you have Calabi-Yau twofold, which is K3, then this extended out, so now we call this as extended n equal 2 by adding this additional operator. And in this case, this extended algebra is called n equal 4 superconformal algebra. So you have, in addition to Virasoro generator and the standard n equal 2 superconformal generator, in addition, you have another set of superconformal generator and another pair of current. And this original current together with this these 2 additional current give rise to n equal SU2 affine Lie algebra. Now, if you have n equal 2 algebra, then you can consider highest weight representation. Yes?
This extended algebra, is this, I mean, this is sort of W algebra, nonlinear Calabi-Yau algebra. Or not?
So this one, Right, yeah. So for higher than d equal, higher or including d equals 3, in general, this is a W algebra type operator. Yes. It is only for K3 case it makes a standard Lie algebra type structure. Yes, you're quite right. Because dimension of this operator is large. So D, conformal dimension is D. So it's like W algebra indeed.
There is an analogous kind of algebra, even though you don't have a different in some ways, but you do have an analogous extended algebra of this type for the G2 case as well.
Yes, exactly. I think Kumran and Shatashibiri studied that. Yes, exactly. Yes. So you have G2 manifold. So for this, for every additional structure, you can consider such extended algebra. Yes, those are interesting.
This thing always just comes from constructing the P form with some fermion?
Right, yeah. So typically, yes. And so you have highest weight representation, which means that you consider states, highest weight states annihilated by these operators. And then, of course, eigenvalue of these highest weights are given by delta and Q. But we are also interested in chiral or BPS state. And these are satisfy additional conditions, for example, in the NS sector, which I will be working mostly because of the spectral flow, it doesn't matter whether we work on NS sector or Raman sector. But if you are interested in chiral sector, it is annihilated by additional supercharge, either plus or minus. And so this condition requires that the conformal weight and U1 charge are related by this relation. So this is called BPS bound in this case. So Taormina and Eguchi studied representations of these types for n equal 4 superconformal algebra. And this was extended by Odake to higher dimensional Calabi-Yau. So there are they classified the representation and computed characters. And as I advertised at the beginning, these characters are expressed in terms of mock modular forms. And so for chiral or BPS representation, you have characters, which I'm going to denote chi of Q. And I would like to remind you that delta is half of Q in this case. So in this case, actually, the number of chi's is D, where D is a dimension of Calabi-Yaus. For non-BPS, I'm going to denote the character by Q and delta, because then there are no obvious relations, except that delta is bounded from below by half of Q. And then there are D minus 1 of them for each Q and delta, for each delta, excuse me. So for each, so for chi's, so I should say for each. So for BPS characters, there are D of them, period. So there are D choices of Qs.
D for Calabi-Yau D.
D for Calabi-Yau D. And non-BPS ones, for each delta, there are D minus 1 choice of Q.
This is separate than the left and the right sector?
Yeah, so I'm just writing the holomorphic part of it. So the task is to find modular invariant combinations of these fellows. And the reason that you have one less object like that is because there is a constraint by topology. So so there is a width index you can compute. So if you compute index of chi of Q, obviously the non-BPS one doesn't have width index. This one has width index in the sense that if you float the Raman sector and count the number of ground state. you can compute the index. And so this is equal to -1 to d minus q for q positive, 1 plus -1 to the d for q equals 0, and -1 to the q for q negative. So you have a non-zero Witte index for the BPS sector. And so then the following question arises. So suppose, for example, you take this non-BPS character and hit the BPS bound, then one should be able to express that in terms of BPS characters. Because BPS character that's spanning state with this bound.
How does it hit the bound? Doesn't that spiral?
Yeah, so suppose delta hits this one. So then you can ask what happens. Then what happens is that, for example, if you have character non-BPS character hitting this bound, like that, for example, then what happens is that it becomes chi of plus minus q plus chi of plus minus q plus minus 1, depending on the sign of q, I think.
No, I'm confused about something.
Yeah.
Aren't these become ground states?
When q is 0, it hits the ground state.
No, ground state in the Raman sector, I meant.
Yeah. So okay. So if you, that's right. So in the Raman sector, so this one has all in the ground state. So it's going to be like that. And the massive one is there is a gap to it. So
actually,
yeah. That's not a problem.
What are the examples? I didn't know there were examples where this happened.
So this is an example. So
I mean, is there a Calabi-Yau, which you have a massive thing becomes massless?
Yeah. Because if you take the large volume limit.
No, I mean, as an infinite limit, I can understand. But
yeah.
In conformal theory, I find this is a modular. Does this ever happen?
No.
Okay.
No.
I thought it was
But representation theories are prepared in case Calabi-Yau becomes infinite volume. I mean, it has to be prepared for anything. I mean,
But you would not use these deltas in your constructions, the ones which are equal to half q. I mean.
So for example, if you take if you try to construct a modular invariant partial function of Calabi-Yau manifold, and then so then you're going to use this, and for compact Calabi-Yau, the value of allowed value of deltas are discrete. And but if you take the size of Calabi-Yau larger and larger, you'd increasingly in need to have non-BPS character with delta minus half of absolute value of q, smaller and smaller.
Yes.
And then in the limit, we have to have in a situation where this hits 0. So that means that you need to have a representation which does that.
But I don't understand. That's precisely the question related to whether you're interested in non-compact Calabi-Yau. You said you're not.
I'm not. But you can have a series of compact Calabi-Yau which are increasingly non-compact.
But you never have a delta equal to half q.
But it can be epsilon away from q, half of q.
Right, you can be epsilon away.
Yes.
And so your consideration only applies for epsilon away in this context.
But in fact, these relations are important later. And so for example, for even in the limit when q equals 0 and delta equals 0, there are relations like that. So if you have that, you have chi 0 plus chi 1 plus chi minus 1. So you see that if you hit this BPS bound, all the non-BPS character become linear combination of BPS character, but in a way that Witte index cancels out. If you compute the Witte index, you can check that Witte index is cancelled out. And so that's why you have one less representation compared to the original representation, because this is constrained by Witte index. This is constrained by the fact that Witte index has to cancel out. So there is one condition, so that's why you have one less characters. So now let's discuss the structure of the partition function. Oh, by the way, it's too bad. So I should have, of course, said at the very beginning that this work is in collaboration with Christoph Keller, and the paper should appear at any moment we are writing it. So I apologize to Christoph that I didn't say it at the very beginning in case he's listening to me.
Sorry, just want to make sure I understand these numbers. Number of chi's is d and so on. If you look at the BPS ones, I thought that these have to do with the charges, whether it's from 0 up to
Yeah.
-1. But for the non-BPS, you're still getting discrete. What does that d-1 mean even?
So for each delta, there are choices of Qs that you can choose. So I can spell this.
For each delta,
I can spell this out. But for example, for chiral ones or for BPS ones, Q can be 0 plus minus 1 up to d over 2. And then for non-BPS,
I see.
the same thing, but d minus 1 over 2 or something like that.
So the Q is the variable. That's
Q is a variable. So for each delta, you can have d minus 1 choice of Qs. Okay, so now we are interested in structure of partition function of this two-dimensional conformal field theory, which is basically the Hilbert space of conformal field theory are representation of two pairs of superconformal algebra. So that means that partition function can be expressed as sum of product of characters, and it can be in the product of chi and chi bar, which are BPS characters, or chi non-BPS character and BPS one, or vice versa. And then also this combination. So you can call that as BPS or half BPS. And you can call that, because each one of them preserves half of the supercharges, you can call that as quarter of BPS. And then this one also, different quarter. And then this one is non-BPS. Yeah?
So if you look at off-shell superfields in 2 dimensions for 2-2 systems, there's a closely corresponding description in terms of chiral and semichiral.
Okay. I don't know what semichiral means.
Semichiral means left chiral but right unconstrained.
Oh, okay. So those are probably those kind of fellows. Yes. Thank you.
But there's a further distinction because there's a sign assignment, between chiral and twisted chiral. Does that arise here?
Chiral and twisted chiral. Are these like distinction between left and right?
No, that's in the half BPS. Chiral means you have things that are left chiral and right chiral.
Oh, yeah.
And have left
Okay.
chiral and right anti-chiral.
Sure. Yeah, yes. So there are, these correspond to charge, whether charge positive or negative, and those kinds. Yes. So I will actually describe that right now. So this one, for example, has this structure that you have a unique vacuum state. The ground state is always, NS ground state is always unique. And then you have a non-trivial combination of chi q and chi q bar. And you sum over charges which are non-zero. Now, if you assume that n equal 2 extended chiral algebra is the largest chiral algebra you have for your theory, then you cannot have cross-term between the vacuum representation and other non-trivial representations. I'm going to assume that for now, although I can relax this assumption and still get similar result. But for the because of the interest of time, I will assume that there is no cross-term between the vacuum representation and other representations. If you don't assume that, the chiral algebra should be further extended. And for non-compact Calabi-Yau, something like that happens. But for compact one, generically it doesn't happen. And this multiplicity NQQ bar are all given by Hodge numbers. So for example, in the case of Calabi-Yau threefold, this Z chi bar is given by chi 0 bar plus H11 Hodge number of chi 1 bar plus chi 1 minus 1 bar plus H21 chi 1 minus 1 bar plus chi minus 1 chi 1 bar. So this answer, I hope, the question of Martin, because I think that these are, in your terminology, chiral representation for both left and right, whereas these are the other ones. And so these are a combination of chiral ones, and these are combination of chiral and twisted chiral ones. And so that distinguishes the two types of Hodge number that you can have for Calabi-Yau threefold. Does that answer your question?
You don't have a minus one?
It's right here. Oh, I'm sorry. Like that. So there are 4 combinations, and those 4 combinations appears like that. So mirror symmetry exchanging the chiral and twisted chiral ones.
And then just parenthetically, I guess it's clear to the experts, but I just want to point out that in your chi0, chi0, you have H03 and H33 and H30 as well, because of spectral flow.
Right.
So you don't need to describe that. All the cohomologies.
Oh, yeah, that's right. So, okay.
This isn't enough to restrict the Hodge number? Does it say something about the Hodge numbers?
Well, Hodge numbers appear as multiplicity of a particular BPS state. And so that's always the case that for general Calabi-Yau manifold, you have enough choice of BPS state to distinguish all different Hodge numbers.
Sure, but you can't say general properties about the Z and use that to say something.
General properties.
Kinds of limits that
He's
you
going there. Well, he's going to restrict them by H's now. I guess that's.
Yeah. So this part is completely sort of topological, and so we're going to use this kind of knowledge to constrain other things. So now let's move on to the mixed combination. This combination, which is a quarter BPS sector. And so I'm going to argue that this part is essentially determined by the elliptic genus of Calabi-Yau. So you can, of course, first write down parameterize what this is. So chiral one is completely determined by the charge, but non-chiral representation, you need to specify charge and conformal weight. So you can write it in this way. So this is this mixed term, and this is, as I said, is quarter BPS sector. So now what you do is you keep this in the NS part, and you keep that you flow that to Raman sector, and moreover you include -1 to the F to it, so that you turn this into Witte index. So by spectral flow, you can turn this into Witte index. And so that the resulting quantity is called elliptic genus. So maybe it's instructive to write this. So if you flow this, so that this is turned into Witte index, then you get some holomorphic object, which I can write explicitly So it can be expressed as sum over characters. So the detail is not important, but I just wanted to say that all these are expressed in terms of multiplicity that appear in this half and quarter BPS sectors. And but the important thing is that it is actually transformed by itself, transforms nicely under modular transformation, because original character is modular invariant. Original character is modular invariant, and then if you flow this part to Witte index, it is a number, so it should be modular invariant by itself. So the remainder should transform nicely under modular transformation. I should say that in order to get this J, I should also add Z chi bar. the non-BPS sector won't contribute to spectral flow. So this, considering contribution from this part is enough. So then you get some holomorphic object which transforms nicely under modular transformation, which preserves the spin structure. And so these are called weak Jacobi form. Of weight 0 and index d over half, where d again is a dimension of Calabi-Yau manifold. And the important thing is that the dimension of this space is finite. So you have a finite number of them. And so that's great, because if you have finite number of them, then if you can fix the normalization appropriately by just looking at the first few terms, then you know that all the elliptic, you know that you have fixed the elliptic genus completely, and then you know the rest of the number. So let me give you an example of how you do that. So let's first consider the case of case 3, which is d equal 2. Okay, so now in this case, actually there is a unique Jacobi form. So the Jacobi form is unique, but then what we know is that J, well, it should start from, well, the important thing is that these are unknown numbers. But this number, the coefficient in front of this is known, because we assume that there is a unique ground state in the NS sector. So the multiplicity here should be 1. So that means that in even dimension, multiplicity is 2. So that means that chi naught should always appear with multiplicity 2. And that completely fixes this one already. So we know what it is. So once we know what it is, the rest can be completely determined. So for example, from that, we know that the coefficient of chi 1 is 1. Chi 1 is 20. And in fact, this should be, by comparing that with this multiplicity, we know that this should correspond to H11. So you can derive that H11 of K3 is 20 by using modular invariance and the property of elliptic genus. And then you go on, and you can compute the expansion for the rest.
There must be a choice that you made some. Oh yeah, because
You said 2 instead of 0. So T4 distinguishes that.
Yeah. That's right. So I assume there is no cross term. So for T4, there is a cross term. So that distinguishes the two.
you can also
Distinguish that there's only other choices T4.
Sorry? Yeah. You can prove that if you assume that D equal to Calabi-Yau condition, there are only two solutions. One is this, and the other is a torus.
So this tells you there are no non-geometric CFTs with this.
Yeah. Well, if you say this is already geometric, yes. And then you can expand it in this way.
What about, one of the things I'm confused about is, if you look at sigma models and you look at off-shell superfields that correspond to these things, chiral and twisted chiral, then in general you don't have just metrics, you also have B fields and the geometry is changed. So for example, S1 cross S3 has an N equal 4 SCA on it. How does that fit into this story?
This holds for all value moduli, including the turning on of B field.
But I'm not turning on a flux, I'm turning on an H.
Yeah. So this is true for globally for moduli space of Calabi-Yau, including turning on constant. Sorry?
Those are not Calabi-Yau. So what happens with S1 cross?
It also doesn't have the central charge that you think.
Right,
because
yeah,
of
you have to
WZW.
put in a background charge
Oh, you're talking about turning on flux, not on the constant B field.
Right.
Okay. So then it's not CFT anymore.
Well, it
Well,
is.
that's 3 times S1, it's a CFT.
What central charge does it have?
It doesn't have C hat equals.
Well, because it's a
4.
WZW model, so it depends on K.
No, but central charges for the algebras he's talking about are all integral.
I know, I understand.
What is the value of the dimension?
You can make it integral by turning on a background, decompactifying the S1.
He's
turning
claiming
on a
that if you
background
made it
charge.
D equals to 2,
But
you're
then it's
going
not
at these.
compact, I see.
Either it's compact or it's not.
Right.
If it's not compact, it's not saying anything.
Okay. Yeah, I guess that would have to be.
I don't know both terms.
Yeah. Okay.
So you can expand this quantity, and then this n is given by this cross term. So delta equal n, q equal 1, and q bar equal 1, minus n of delta equal n, q equal 0, and q bar q equal 0, and oh, excuse me. Maybe I shouldn't write it in this small corner, so because this is relevant. So this is this thing is n of delta equal n, q equal 0, q bar equal 1, minus n delta equal n, q equal 0, and q bar equal 0. Okay, so that means that by just by taking advantage of the fact that the weak Jacobi form of weight 0 and index 1, there is only one of them, you can completely determine this by knowing the multiplicity of the vacuum to be 1, and the rest is determined. H11 is determined, and then also this kind of combination of cross term between BPS representation and non-BPS representation is determined, but with this in this combination. Now, in my PhD thesis in 1989, I conjecture that actually all these numbers are positive. And the reason I made this conjecture is that if you, so this number is completely determined because this is known, this is a completely simple function. And so you can derive this. So the conjecture was this is positive because if it was negative, if there was particular n, small n, so that this is negative, it would have to mean that you have to have this to be non-zero for globally for the moduli space of K3. But this is a crossing between non-BPS representation and the vacuum representation. So that means that if this is non-zero, that means that the symmetry is enhanced above n equal 4 superconformal algebra. And since this should be if that was the case, it should be true for any part of the moduli space. So that means that generically symmetry chiral algebra should be enhanced to be greater than n equal 4. And I thought that was unlikely. So I conjecture that given that, all these coefficients has to be positive, non-negative integers. And I checked this for small n up to 100, and then they all turn out to be positive integers. And so in my PhD thesis, I have this list. These numbers. And after 22 years, 22 years after my PhD thesis, Toru Eguchi and Yuji Tachikawa and I realized that all these are dimension of irreducible representation of the largest Massieu group, M24. And we still don't understand why that is the case, but it turns out that the first 5 of these numbers are all dimension of irreducible representation of dimension of irreducible representation of M24. And the higher one can also be simply expressed as sum of a small number of those dimensions. And but these are just dimensions. But more recently, Matthias Gabadiero and other friends show that some similar that also holds for the level of characters. Namely, if you can twist this elliptic genus to include non-trivial element of group element of M24, and actually that completely specified how these number can be decomposed into reps. So that indicates that not only these are all non-negative number, but these are actually dimension of these interesting groups. And so I think it's sort of interesting to explore this further. So this is by myself with Eguchi and Tachikawa. Okay, so now you can ask what happens in the case of.
I think it's also been interesting work by Miranda.
Yes. Yes. So I think that considering not dimension, but twisted character, I think was first explored by Miranda, and it started out to have interesting. So that actually was very powerful way. So to determine how these numbers are decomposed into small number of dimension of irreducible representation of M24.
Is the other part of your conjecture that the N00 is always 0?
N00.
Q equals 0, Q bar equals 0.
This one.
Yeah,
So my real conjecture is that this should be always be 0. So the corollary of that is that this should be always non-negative numbers. And so that was what I checked. And you can check it by computing the first few terms. Or you can also check the asymptotic behavior of this number, which is also, you can easily evaluate by modular transformation. This turned out to be positive, but more recent conjecture means that it says that not only these are non-negative integer, but that integer has some interesting algebraic meaning to it.
Do you have a similar conjecture for a higher central product?
I think the situation is not clear. I think there has been some work on expanding, more generally expanding weak Jacobi form in terms of mock modular forms. And then there appear some other interesting finite groups, I think. Probably you are more familiar with that than myself.
Yeah, in our paper also, all the cases we found out.
But are these necessarily related to Jacobi form, or they're related to elliptic genus, or generally about Jacobi forms? Yeah, because what I found mysterious is that for those general cases, these Jacobi forms are not necessarily related to elliptic genus, so suggesting that maybe the object we should be looking at is not necessarily Calabi-Yau compactification, but something different or something larger. I don't know. Thank you for pointing that out. So, so this is for case 3. And then the second example for elliptic genus is Calabi-Yau threefold computation. So in this case, the special feature is that the index for the vacuum representation is 0. So we cannot use this trick to use the multiplicity of the vacuum representation to fix the normalization. Now, by the way, in this case, the dimension of the relevant weak Jacobi form is also 1. So if you know the normalization, you can fix it. Okay. But for a long time, I thought that this wasn't an interesting case for 2 reasons. One is that index for the vacuum representation is 0, and the other is well, there's the other reason I'm going to tell you about. So, but anyway, so if you can still write the formula. So the vacuum representation does not contribute, so that means that you have to go to the next level. So the coefficient of that is proportional to Euler characteristic of the target Calabi-Yau manifold. And then you have again something like that. So you can write the BPS part and non-BPS part. You can write the sum elliptic genus as sum of a BPS part and non-BPS part again. And although we cannot use a vacuum degeneracy to fix the elliptic genus, but we can still utilize the fact that the coefficient of BPS part is given by this the difference of the Hodge numbers, the Euler characteristic. So if you know the topological type of Calabi-Yau manifold, then you can fix this quantity, and then you can try to know you can know about this combination. So that's interesting. But what I found rather surprising was that this is actually Jacobi form by itself. So this is actually rather significant. This is rather significant because So there is a unique Jacobi form phi 0 3 half, which is the Jacobi form of weight 0 and index 3 over half, which is relevant in this case. And it turns out that this is actually equal to this one. So what does it mean? Well, it means that the Jacobi form has to be this times this quantity. So that means that this has to be 0. So that means that by knowing this, one can deduce that but these has to be equal. So if these are equal, then what it means, well, these quantities appears in the cross term like that. But q bar equal 1 and q bar equal minus 1 appears in the same combination. So that means that this is equal to sum of q and the delta, and then n delta q of 1, and then you have ch of q delta times chi 1 bar plus chi 1 minus 1. And of course, there is an additional thing, which is n delta q bar equals 0 of ch of delta q of chi of 0 bar. So you can, from this, you can deduce that it has to have this kind of structure. But then, if you remember what I wrote earlier, which I think I erased, which is that this is actually the combination of massive character. This is equal to ch of 1 bar. So you should think of this as massive combination. Namely, this is actually non-BPS combination. The other one is a cross term between non-trivial representation and the vacuum representation. So if you assume that the chiral algebra is not extended, then this should be 0. So from that, one can conclude that for Calabi-Yau threefold, if you assume that n equal to SCFA is not extended, namely there is no, extended n equal to is not further extended, then the cross term should vanish. And so this is a very useful result. And so I'm going to utilize this.
The mixed term that you said, I guess you raised the integral, the fact that the which Jacobi form was unique led to some identities.
Yes.
Does that have interpretation in terms of representation of n equal to algebra or not?
It has a representation.
Can you prove why that had to be the case?
Well, I had to use modular invariance to derive.
Direct interpretation from universal algebra, because you're saying something about representations. You're saying it doesn't follow from representation itself.
It doesn't follow from representation. In fact, I think that, for example, for toroidal compactification, you can have such mixed term.
Because you have more symmetry.
Yeah. So therefore, this, it cannot just follow from algebra. It has to follow from modular invariance plus some additional geometric consideration, such as amount of symmetry that you can.
I misunderstood. I thought the previous statement that you were saying that the fact they are equal didn't follow from any assumption, right? From the uniqueness of Jacobi form it followed, right?
Which one being equal?
The one you erased, the two equations.
Yeah. Well, that follows from uniqueness of Jacobi form.
That's
But
true for T4 also, no?
I think that for T4, probably.
For T4, the first term was 0.
First term is also, everything is 0, yes. I think.
For T4 is true too.
I think so, yeah.
So the statement is true for any case.
Except with this except for
Where
this.
did you make that assumption in the previous statement?
No, I didn't make that assumption. So this up to this part probably it's true also for toroidal compactification.
And that statement doesn't follow from the characters.
Not character alone. I think I'm using modular invariance. So.
Not CTP or anything like that.
No, I don't think so. Okay, so let's see where we are.
Take a break if you think this is a good point for.
Yeah, I think it's a good point to take a break because the rest is so this is basically I summarize what is known, and then so I'm going to tell you what was not known from now on. But I think it's a good place to take a break. Thank you.